Good evening. We are now starting the fourth chapter, Law Motion in a Plane. That is the fourth chapter in your NCERT textbook. Okay. Now, we start the chapter by differentiating between scalar quantities and vector quantities, which I think you are familiar with. Anyway, we will discuss the difference between scalar quantities and vector quantities initially as we start the chapter. If you're looking at scalar quantities, they have only a magnitude and their direction is not important there. Quantities which can be expressed using their magnitudes alone are called scalar quantities. For example, if you're talking about mass, its magnitude. If a body weighs 300 grams, all you need to represent the mass is the magnitude of the mass, and such quantities is what you call as scalar quantities. Example, time. Time also you will see, suppose I say, let's say 1 hour. The magnitude of time is sufficient to express that quantity completely, and quantities, physical quantities whose magnitudes alone is required to represent that quantity completely is what you call as a scalar quantity. When you come to vector quantities, the direction as well as the magnitude are important. For example, if you're talking about displacement, you need to give the direction, because for example, suppose a body starts at point A, moves to the right for 3 meters plus 3 meter, and then it moves back to A, which is you assign a direction to it, and because it's moving to the left, we assign a minus sign. You say if the body comes back to the point A, then the displacement is 0. So in this case, the direction in which the body is traveling along with the magnitude of the distance covered is important, and therefore displacement becomes a vector quantity. Whereas in the same problem, if you do not assign directions, you're just talking about the total magnitude of the body, the distance the body travels, then 3 plus 3 would be 6 meter. That will be the total distance traveled by the body. So distance becomes a scalar quantity, whereas displacement becomes a vector quantity, because when we looked at the distance traveled, we took only the total magnitude, not the direction. But when we talk about displacement, we assign a negative sign showing that we are including not only the magnitude but also the direction of that quantity, and therefore displacement is a vector quantity. So the quantities in which both magnitude and direction are important is what you call as a vector quantity. Similarly, when you're adding scalar quantities, we simply use algebraic addition, whereas when we add vector quantities, we will be using vector addition, which I will be teaching you in this chapter. Now, before we move on to the addition and subtraction of vectors, let us first discuss what you mean by the position vector of a body. The position and the displacement vector. So this whole chapter we are talking about motion of a particle in a plane. In the previous chapter we discussed about motion of a body in a straight line. That means either it is moving along the x-axis, or it is moving along the y-axis, or it may be moving along the z-axis. The body is just moving in a straight line. Now here the body is moving in a plane. Let's say this is the y and this is the x-axis. So the body moves, if it's moving here, it's moving in the xy plane. For example, if an ant is moving on the floor of your room, then let's say this is the floor of your room. Okay? Let's take this as the x-axis and this as the y-axis. So if the position of the ant is here, it will have a coordinate, a x coordinate. It will also have a y coordinate, and therefore you can say that this position of the ant is in a plane with an x coordinate and a y coordinate. On the other hand, if the ant is just moving along the x-axis, then it is called motion in a straight line. So in this chapter we are going to discuss motion of a particle or a body in a plane. We select the xy plane. It could be the xy plane. The z-axis is like this, perpendicular to the xy plane. So it could be the YZ plane or the XZ plane. Okay, for convenience, I'm just taking the XY plane. Now let's say a body at some time t1, the body's position is here. So this is the position of the body. So this is the origin of the coordinate axis. A line drawn from the origin to the position of the body, represented by an arrow mark like this, gives the position vector of this body. So because we call the position a vector here, it has magnitude and direction. The direction will be given by the angle theta that this body makes, or this line makes, the position vector makes with the positive x-axis. For example, if it is theta 60 degree, you may say that the position of the body is at 60 degree with the positive x-axis, thereby correctly giving a direction to the position. And the length of this line that you draw will give you the magnitude of that position vector. For example, let us say this is, I say 1 centimeter. Let's say this is 5 centimeter. Okay. So the length of that vector will give you the magnitude of that position vector. Theta will give you the direction of that position vector. For example, I told you if this makes 60 degree, we know that the position of the body is at 60 degree with the positive x-axis. Okay, so this is what you call as position vector, any vector that joins the origin to the position of the body at that time, whose length gives you the magnitude of that vector and theta gives you the direction of that vector. Now we are going to discuss what you mean by the displacement vector. So let us say that this body was initially at time t1 at this position P. After some time the body moved and let's say reached here at new position Q. So if I draw a line from the origin to this point P, that is called the position vector at time t1. After some time t2, the position vector has changed. This line that is drawn from the origin to that new position is what you call the position vector at time t2. The displacement vector is the vector that joins the initial position to the final position here. So this PQ that starts from the initial position and ends at the final position is what you call as the displacement vector in the time interval t1 to t2. Whereas OP is called the initial position vector and OQ is called the final position vector at time t2. Then we need to know what you mean by equal vectors. Naturally, the word itself suggests that equal vectors would mean two vectors that have the same magnitude and same direction, because I told you vectors have both magnitude and direction. So if you say two vectors are equal, then naturally they must have the same direction and they must also have the same magnitude. For example, suppose I draw two vectors like this, two vectors P and Q, both of them having the same length, which means they have the same magnitude, and let's say both of them make the same angle theta with the positive x-axis, so they have the same direction. Such vectors are what you call as equal vectors. Then we have what you call as unit vector. Like I told you, a vector has both magnitude and direction. So if I write a vector, then this represents a vector A. That sign, that arrow mark on top tells you that it's a vector A. This has a magnitude, let us denote it by simply A, means magnitude of this vector, and the direction will be given by A cap. Now let me explain to you what you mean by this A cap. Now this A cap is a unit vector, that is a vector whose magnitude is 1 but has the same direction as this vector A. For example, in our xy plane, suppose I represent this is vector A. Okay, let's say this is 5 meters length. I take 1 meter here and that makes an angle theta here, and this is what you call as A cap, meaning this A cap is a vector that has the same direction as vector A, right? This is the vector A that we are talking about. The vector A is this, right? It makes an angle theta with the x-axis. It makes an angle theta with the x-axis. So does the unit vector, makes the same angle theta with the x-axis. But the unit vector has a magnitude of, this is just 1 meter, and vector A will be multiplied that many times. That means if its magnitude is A, then vector A will be represented in magnitude by A. For example, I told you if it's 5 meters, A cap is only 1 meter. So the total vector should be 5 A cap. What does that mean? This is A cap is having unit length 1 meter. So your vector A has 5 times that, 5 meters. But it has the same direction as this unit vector. Both of them make angle theta with the positive x-axis. So, unit vector A cap is simply vector A divided by the magnitude A. So, if you look at this is vector A, having both magnitude and direction. Its magnitude is just A without the vector sign on top. This A cap represents a vector which is in the same direction as this vector but has a magnitude of 1. Now, as we go into this chapter, remember we have the x, y, z axis. We have the x-axis here, the y-axis here, and the z-axis, which you know is perpendicular to the xy plane. But when I draw it on the board, this is how I will draw. Okay. Now, this is the x-axis. A unit vector along the x-axis is represented by I cap. So, if you see, let's say 5 I cap, please remember, it represents a vector whose magnitude is 5, whose direction lies along the x-axis, because I cap is a unit vector along the x-axis. A unit vector, I told you, has unit magnitude, 1 meter, unit length. I cap means direction is along the x-axis. Then, a unit vector along the y-axis is represented by j cap, which means if you see vector A represented as 10 j cap, it means that this vector A lies along the positive y-axis and has a magnitude of 10. If you see negative sign, it means it lies along the negative y-axis. Similarly, a unit vector along the z-axis is represented as k cap. Okay, so k cap, if you see k cap, you should know that particular vector, the direction is along the z-axis, minus k cap will be along negative z-axis. J cap is a vector whose magnitude is 1 but direction is along positive y-axis. Minus j cap will be along the negative y-axis. Similarly, if you see I cap, please remember its magnitude is 1, direction along the positive x-axis. Minus I cap would be a vector with magnitude 1 but direction along the negative x-axis. Now we go on into the addition of vector addition. I told you if you're dealing with scalars, we simply do algebraic addition. That is, if we have two positive values, add and put the positive sign. Two negative values, add and put the negative sign. One positive, one negative would be subtract and put the sign of the bigger one. That is algebraic addition for you. When we deal with vectors, we need to learn how to do vector addition. The first law in vector addition is triangle law of vector addition, which simply says, suppose you have two vectors. Let's say we have a vector A and we have a vector B. Okay. You want to add these two vectors. So if you want to add these two vectors, let's say it looks like this, vector B. If you want to add these two vectors, you just need to bring these two vectors to form the adjacent sides of a triangle. So you may shift a vector wherever you like, provided you don't change its magnitude and you don't change its direction. Okay, so suppose let's say this is theta. Theta, let's say, is 60 degree and its length is, let's say, 5 centimeters. I can shift this vector wherever I want, provided I don't change its length and the magnitude and the direction. So what I can do is redraw the vector or shift it in such a manner that it's here, its length remains the same, 5 centimeter, and it makes the same angle theta, that is 60 degree with the positive x-axis. So then you have shifted the vector, but you have not changed the vector. So now you've brought vector b in such a manner that it forms the adjacent sides of a triangle in the same order. That is, this is called the tail to head and then tail to head. This is going in the same order. Then the closing side taken in the opposite order will give you the resultant vector. That is, adding the two vectors. Taken in the opposite order would mean, see, suppose I draw a vector like this, a vector like this, and a vector like this. Then all the three vectors A, B, and R are in the same order. You see, A to B to C, A like this, same order B, same order R. You're going in the same order. Opposite order R would mean A and B are in the same order, but R is in the opposite order. So in triangular law of vector addition, I've printed it there for you. If two vectors can be represented both in magnitude and direction by the two sides of a triangle taken in the same order, then the resultant is represented by the third side taken in the opposite order both in magnitude and direction. So this is triangular law of vector addition for you. Simply, when you want to add two vectors A and B, let them both in magnitude and direction represent the adjacent sides of a triangle, the sides of a triangle. Then the third side, which is taken in the opposite order, will represent the resultant vector both in direction as well as magnitude. Okay. Then we have something called as the parallelogram law of vector addition. Now, before we go into parallelogram law of vector addition, I will introduce another topic called resolution of vectors, after which we will move into parallelogram law of vector addition. So, now we have the xy plane, this is the y-axis, this is the x-axis. We have our vector, let's say I am calling this vector A. Resolution of a vector A would mean splitting this vector A into two rectangular components, one component along the x-axis and the other component along the y-axis, so that if you combine the two components, you will get the resultant vector A. I repeat, resolution of a vector here, let's say example A, resolution of a vector A would mean splitting this vector into two rectangular components, one component along the x-axis, the other component along the y-axis, such that if you add the two components, you should get the resultant vector A. That is what you call as resolving a vector A or resolution of this vector. Let me take this component along the x-axis has a magnitude AX. So I am not putting the vector sign on top of it because this is just the magnitude of this vector A along the x-axis. Okay? And because it is along the x-axis, I need to put I cap to give the direction. So there is the magnitude and the direction together make it the component vector along the x-axis, component of A. Similarly, let this component along the y-axis have a magnitude AY with the direction naturally given by J cap, because I told you J cap has unit magnitude, it's along the positive y-axis. So the two components of this vector A, the component along this x-axis has direction naturally I cap, because I cap represents a unit vector whose magnitude is 1 but direction is along x-axis. its magnitude along the vector, the component of this vector along this x-axis has a magnitude ax, and the component of a along the y-axis has a magnitude ay. So if you combine these two, you must get the resultant vector A. By triangular law of vector addition, we know, so if this is a by j cap, this is also a by j cap, because these are the parallel sides. So now the direction of this vector, this component should be like this, and this component like this. Okay. So if you draw a by ax I cap like this, a by j cap like this, they have formed the sides of a triangle, and the resultant of these two will be given by the third side taken in the opposite order. So that ax I cap plus ay j cap must give the resultant vector A. By triangular law of vector addition, what did I teach you? The vector here, ax I cap plus ay j cap, both form the sides of a triangle taken in the same order. The resultant of these two must be represented by the third side taken in the opposite order, so that we may write ax I cap plus ay j cap, the resultant is vector A. Okay, so this is what you mean by resolution of vectors. You may resolve a vector A to two components, one along the x-axis and the other along the y-axis, so that the combined effect of the two vectors will be giving you the resultant vector A. Now to find out the magnitude, let us take A making an angle theta here. Okay, theta here. Now, what is sine theta from this? Sine theta, as you know, is opposite side by hypotenuse. So if I am taking just the magnitudes, sine theta opposite side, magnitude is only ay, j represents the direction, and the magnitude of the hypotenuse here for this triangle is simply a without the vector sign. If it's a vector, it is magnitude plus the direction. If I simply write a, it means it is a magnitude. So sine theta is opposite side by hypotenuse, which is only the magnitudes I've used. So the magnitude of ay, that is ay, which is the magnitude of the component along the y-axis, is a sine theta. Right? Similarly, if you take cos theta, this is equal to, cos theta is adjacent side by hypotenuse. The adjacent side here is in magnitude ax, and the hypotenuse has a magnitude a, so that you may write ax is equal to a cos theta. So remember, whenever you resolve a given vector, that vector that is being resolved forms the hypotenuse of a right angle triangle. You see, this is the right angle, 90 degree. Opposite to that we have the hypotenuse. So you always resolve the vector which becomes the hypotenuse of the right angle triangle, and the ay is called the vertical component or the opposite component. Opposite component because this side is opposite to angle theta. So the opposite component ay is always a sine theta. Similarly, the adjacent side, ax is called the adjacent component or the horizontal component because this ax is adjacent to angle theta, will be a cos theta. This is what you mean by resolution of vectors. Now, let me also show you one thing. Here we have, this is a right angled triangle. You may apply Pythagoras theorem here. What does Pythagoras theorem say? Square of this plus square of this must be equal to the square of this, which means this is what ax square plus ay square must be equal to a square. Let's check that. Ax is what? A cos theta. So that is a square cos square theta plus ay what? A sin theta, which is a square sin square theta, must be equal to, what is that equal to? I'll take a square outside, cos square theta plus sin square theta, that is 1. So that's equal to a square, and that's what we needed, a square. So we have proved that if you take Pythagoras also, you take this square plus this square, you're getting the square of this. Okay. Okay. Then let me just give you one more example for a solution. Suppose I tell you this vector represents force vector. This is force, making an angle 60 degree. Okay. Now this force vector has a magnitude fx along the x-axis and the component fy along the y-axis. So if you are going to resolve this vector f into two components, the component along its x-axis is called fx and the magnitude of the component along the y-axis is called fy. To find out fx, what do we have? Fx is equal to, let's say this force is 5 Newton, that is, magnitude is 5 Newton. Then this will be F cos theta. The Fx along x-axis, it's the adjacent side, so the adjacent component will be cos theta. So this will be 5 into cos 60, which will be 5 into half, and that will be 5 by 2. So this will be 5 by 2 Newton, and the Fy will be the opposite component, because I told you the Fy is the opposite to theta. That's called the vertical component or the opposite component. So Fy is equal to 5 into sin theta, that is 5 into sin 60, that is 5 into sin 60 is root 3 by 2. So this component is 5 root 3 by 2. And if you combine this two, and you will get the resultant vector f. Is that clear? One more example so that this is clear to you. Suppose I have a vector like this. This is theta. Okay. This vector I am going to call as B. Right? Now, I told you if you are going to resolve this vector into two components along the x and y axis, this will be the hypotenuse of a right angle triangle. So let me complete the right angle triangle. See, this is a right angle. Opposite to that we have the hypotenuse. That hypotenuse represents this vector B. So to this angle, this is the adjacent side. This is the adjacent side, and this is the opposite side. The adjacent side I will call as the horizontal component, which is along the y-axis. So you may call this as by along this, but it is the adjacent component, right? So this will be b cos theta. And along the x-axis, if this is the x-axis and this is the y-axis, this component is bx, but this is opposite to theta, and because it is the opposite component, we would write b sin theta. So the two components of vector b are b cos theta and b sin theta. So please note one thing, whether it is by or bx, the side that is adjacent to theta will take the cos theta term, and the side that is opposite to theta will take the sin theta term, and this vector b is the hypotenuse of that right angle triangle. I hope that's clear to you. Resolution of vectors. Now again, we go back to addition of vectors. We finished, I just discussed with you triangular law of vector addition, we now have what is called as the parallelogram law of vector addition. Parallelogram law of vector addition. This parallelogram law of vector addition is essentially saying the same thing as triangular law of vector addition. It simply says, suppose you're going to add two vectors. Let's say you're going to add vectors A and B, which form the adjacent sides of a parallelogram. So you're going to add two vectors A and another vector B. They are going to let them form the adjacent sides of a parallelogram. Complete the parallelogram. Then the resultant will be given by, this will be the resultant, will be given by the diagonal of the parallelogram starting from the origin of A and B. I repeat, if you want to add two vectors A and B, let them form the adjacent sides of a parallelogram starting from a common point O. Then the resultant A plus B, resultant of A plus B, adding A and B, will be represented both in magnitude and direction by the diagonal of that parallelogram starting from that common point O. So, the resultant will be given by the diagonal, that is A plus B, the length of that, the magnitude of will be given by the length of that diagonal, and the direction will be given by the angle that the resultant makes with the x-axis, alpha, for example alpha. So this is a statement for parallelogram law of vector addition. So it will be essentially the same thing that we discussed in triangular law of vector addition, right? Because if this is A, you know this also will be A. Look at this, this is A. So then we see that if you are adding two vectors taken in the same order, B plus A taken in the same order, then the third side of that triangle taken in the opposite order will represent the resultant both in magnitude and direction. So this is the same thing that we discussed under triangle law of vector addition. So parallelogram law of vector addition and triangle law of vector addition essentially saying the same thing, but when you state, you have to state it differently, like I have printed in your notes for you. Now I am going to show you how to find the magnitude and the direction of this resultant R. It's not enough for you to state parallelogram law of vector addition. You need to use this in doing problems. So we need a formula that will give us the magnitude of this resultant R given by the diagonal and the direction of the resultant R given by the diagonal. For that, we are going to add two vectors A and B. Okay, so we have a vector, let's say this is A, vector A, and we have a vector B like this. The two are making an angle theta. Now what does parallelogram law of vector addition say? If you want to add these two vectors, let them form the adjacent sides of a triangle, of a parallelogram. Starting from a common point, you complete the parallelogram. So that the diagonal of that parallelogram starting from that common point will represent the resultant both in magnitude and direction. So now what we need is a formula to find the magnitude of R and to find the direction of R, because we know that this resultant, this diagonal represents the resultant of A plus B both in magnitude and direction. So now I am constructing a right angle triangle here like this, so that I know if this is B, this is also B. Parallelogram, these are parallel sides. If this is theta, then this also has to be theta, because theta is the angle between A and B. So we have A and B making this angle theta here. Let me call this as Q, S, P and N here. Okay. Now the angle theta is the angle between vectors A and B. and this angle is what I'm going to call as alpha. Please note, alpha is the angle that the resultant makes with the vector A. Right. Now, to find out magnitude of R, I am going to apply Pythagoras theorem to this big triangle OSN. So, in triangle OSN, that's what I am going to do. Now, if I am going to resolve this vector B, you see, in this right angle triangle, I told you this is the right angle triangle. Opposite to the right angle triangle, we have the hypotenuse B. So, I can resolve vector B into this component here and this component here. Because this is theta and this is the adjacent side, this will be called the adjacent component, which I told you will be the cos theta term. So, this Pn will be B times cos theta, and to theta this is the opposite side. So, this will be B times sin theta. I hope you have understood. Just now I taught you resolution of vectors. A vector which forms the hypotenuse of a right angle triangle can be resolved into the adjacent component, adjacent to theta as the cos theta term, B cos theta, and the opposite component, the B sin theta term. So now in triangle OSN, Pythagoras theorem I am going to apply. This diagonal square R square is equal to this plus this, that is ON square plus SN square. Right. This square plus this square will be square of the diagonal. Pythagoras theorem. This is equal to ON would be what? Bracket OP plus PN the whole square plus SN square. OP plus PN the whole square plus SN square. What is OP? In magnitude, it is just A. Vector A, magnitude is just A, plus what is Pn? Magnitude is B cos theta. So that is B cos theta the whole square plus Sn we know is in magnitude B sin theta. So that is B sin theta the whole square. Now I am going to open the bracket. So when I open the bracket, this will be A plus B the whole square. So R square is equal to A square plus this whole square will be B square cos square theta plus 2AB. So that is 2 into AB cos theta, 2AB cos theta, plus when I square this will be B square sin square theta. B square sin square theta. Okay. Then I am just going to combine all the terms. This will be R square is equal to this cos square theta plus sin square theta is 1. So that if I take the B square outside, it's B square bracket sin square theta plus cos square theta, that is 1. So I may write A square plus B square cos square theta plus B square sin square theta. Take the B square outside. Inside the bracket you have sin square theta plus cos square theta, that's 1. So simply B square plus 2AB cos theta here. So resultant R in magnitude will be a root of, because this is R square, A square plus B square plus 2AB cos theta. So now if you are asked to add two vectors A and B, and if they have given you the magnitude of A and B, you can easily find the resultant magnitude by using this formula, where A is the magnitude of A, B is the magnitude of B, and theta is the angle between the two vectors A and B. You can find out what will be A plus B. The resultant will be root of A square plus B square plus 2AB cos theta. That is, magnitude of R is found using this formula. So this is what we mean by vector addition. So when you're adding two vectors, the two vectors that are to be added has to form the adjacent sides of a parallelogram, and the diagonal of that parallelogram taken from that common origin O will represent the resultant, and so the resultant is also a vector which has both magnitude and direction. The magnitude of that resultant will be given by this formula, where A and B stands for the magnitude of the two vectors that you're adding, and theta is the angle between the two vectors that you are adding. Now this is not complete because your vector R has a magnitude as well as a direction. So we need to find out the direction. To find the direction, again we go back to our diagram and we say, look at this right angle triangle, triangle OSN, tan alpha. Tan alpha you know is opposite side by adjacent side. So 2 alpha in the right angle triangle OSN, the opposite side is SN. So this is SN by, the adjacent side is ON. SN by ON, which is SN by, this whole ON is what? OP plus PN. So this is OP plus PN. So that tan alpha is now equal to, SN is what? B sin theta. So B sin theta by OP is A plus PN is B cos theta. So you may find out alpha, tan alpha by the formula B sin theta by A plus B cos theta, where A and B, again I am telling you, are the magnitude of the two vectors that they asked you to add, A and B, and theta is the angle between A and B. So you will get alpha. So you may say, suppose for example you get alpha as 45 degree, okay? Then you may say that the resultant makes 45 degree with vector A. So please note, alpha is the angle made by the resultant with vector A. Always remember that whenever you do problems, alpha is the angle that the resultant vector makes with this vector A. So that will be B sin theta by A plus B cos theta. Now, so this is how you will find the magnitude and the direction of the resultant vector when you are asked to add two vectors A and B, provided they give you the magnitude of A and B and also the angle between A and B. Okay. Now we also have what we call as the polygon law of vector addition. So suppose you are asked to add more than two vectors. A and B are just two vectors. You know how to add those two vectors. Suppose you are asked to add more than two vectors. Let's say you have been asked to add 4 vectors. Okay. So then let's say you have A, you have B, you have C, and you have D. You can, I told you, shift all these vectors wherever you want, provided you don't change their direction. You should not change their magnitude. So I can shift all these vectors together such that they form the sides of a polygon like this. Let's say I have shifted A here, B here, C and D. So I have to shift all the vectors such that they form the sides of a polygon. Then the closing side taken in the opposite order. So all these vectors that I am adding, A, B, C, D, have all been taken in the same order. Then the closing side of this polygon taken in the opposite order. That means it can't come like this. If I draw the resultant like this, then all of them are in the same order. So the closing side of that polygon taken in the opposite order will give you the resultant both in magnitude and direction of the 4 vectors that you added. So you see, I have taken the vectors A, B, C and D to be added as the sides of a polygon taken in the same order, but the resultant is a closing side